My name is Tim Dominic, and I am the chair of the AIAA Public Policy Committee and Master of Ceremonies for today's lecture. Thank you for being with us for the 2020 Durand Lecture for Public Service. We will begin our lecture in just a moment, but first, on behalf of AIAA, let me extend a heartfelt thank you to Lockheed Martin, whose incredibly generous sponsorship has made today's event possible. Thanks to them, we are able to network with our colleagues and our lecturers. The Durand Lecture for Public Service emphasizes notable achievements by a scientific or technical leader whose contributions have led directly to the understanding and application of the science and technology of aeronautics and astronautics for the betterment of humankind. Dr. William Durand was a United States naval officer and a pioneer in mechanical engineering. During his remarkable 99-year life, Dr. Durand contributed significantly to the development of aircraft propellers, and he was the first civilian chair of the National Advisory Committee for Aeronautics, or NACA, the former forerunner of NASA. The Institute's Public Policy Committee takes pride in selecting accomplished leaders in aeronautics and astronautics who can share their knowledge with you through this lecture. To introduce our distinguished lecturer, please welcome Joe Landon, Vice President, Advanced Programs Development, Commercial Civil Space of Lockheed Martin Corporation.
Thank you, Tim. I'm Joe Landon from Lockheed Martin, and it is my pleasure to introduce Dr. Robert Braun, Dean of the College of Engineering and Applied Science at the University of Colorado, Boulder. Dr. Braun has more than 30 years of experience as a space systems engineer, technologist, and organizational leader. He is a recognized authority in the development of entry, descent, and landing systems, and has contributed to the formulation, development, and operation of numerous spaceflight missions. Many of us at Lockheed Martin have a long history with Dr. Braun, working with him on aerodynamic entry and aerobraking systems on several Mars missions dating back to his work on the game-changing Mars Pathfinder mission in the 1990s. He currently serves as the Dean of the College of Engineering and Applied Science at the University of Colorado, Boulder. He previously served as a faculty member of the Georgia Institute of Technology and as a member of the technical staff of NASA's Langley Research Center. He will be joining Caltech in the Jet Propulsion Laboratory later this month as Director of Solar System Exploration. In 2010 to 2011, Dr. Braun served as the first NASA Chief Technologist in more than a decade. In this capacity, he was responsible for the development of the agency's technology and innovation policy and programs. He created and led the initial implementation of numerous NASA technology programs designed to build the capabilities required for our nation's future space missions. This activity spans all 10 NASA centers, industry, academia, and fostered partnerships between NASA and other government agencies. Dr. Braun is a member of the National Academy of Engineering, a fellow of AIAA and the American Astronautical Society, and the author or co-author of more than 300 technical papers. Dr. Braun will now speak on space technology and investment in our future. Please join me in welcoming Dr. Bobby Braun.
Good afternoon. It's great to see so many people here today. Can we maybe bring up my first slide? There we go, on the sides there, I see. I don't know if you've noticed, but if you looked at the picture of me in the intro there, I look a little different now, a bit more gray. That picture was taken on my first day in Washington, which was about 10 years ago. On February 1st of this year, in about a month, NASA's space technology programs are going to be a decade old. And so what I thought I'd do here today is walk you through the development, the formulation and the development of those programs, and some of the achievements that the Space Technology Mission Directorate has had over the last decade. What I'm going to be talking about, by the way, is the collection of work by hundreds of people. I certainly did not do any of this on my own. There was a large team that we assembled at NASA headquarters, people who came from industry, from all the NASA centers, from academia, who joined our new operation and created these programs. And of course, technologists at the centers, in industry and academia, really all around the country, that have done amazing things in space technology in the ensuing decade. But let me start with the space technology programs themselves. I know you told me I'm supposed to advance my own slides. So I'm pushing it. Oh, the wrong button though. There you go. That might help. So you might ask, why am I here talking about space technology? Well, let me just start by saying space technology has been an indelible part of NASA and its purpose for existence since NASA was formed in the Space Act of 1958. If you go and look at the Space Act, there are a number of clauses that describe what NASA is supposed to be working on, and at least two of those clauses, number 2 and number 5, talk about improving the technology of aeronautics and space and serving as a leader, that NASA would position the United States as a global leader in technology and the application thereof for peaceful purposes of flight within and outside the atmosphere. Now, it doesn't say in there specifically Space Technology Mission Directorate, but I would posit that there's no element of NASA that is more focused on these two items today than NASA's Space Technology Mission Directorate. Now, the Space Technology Mission Directorate was not the first time that technology efforts were pushed at NASA. To be honest, they've been a part of NASA since its formation, and these programs have existed in a number of different ways. Technology efforts have been embedded within the mission directorates. Back in the 1980s, 1990s, there was the Office of Aeronautics and Space Technology, which became the Office of Aerospace Technology in the late 90s. And so these things have been in existence. People have been doing space technology work at NASA for a long time. But what happened in the mid-2000s is that the administration at that time was pushing to send humans back to the moon, and they were promised a budget increase, which didn't happen. And when that budget increase didn't occur, they kept pushing towards the moon as their prime goal, and they sucked up all the technology efforts. So the Office of Aerospace Technology became what is now the Office of the Aeronautics Research Mission Directorate, but the space technology part disappeared. And it was kind of scattered about in little pieces, but it was hard to identify. If you were a space technologist at one of the NASA centers, you didn't really have a champion in Washington. And it was a difficult time. So that time, starting in about 2006, 2007, that began to occur. And what happens when the pendulum swings like that is immediately the community, and you all are part of this community, the community reacts. And so there were a number of reports that came out in the 2007, 2008, 2009 timeframe about the importance of a NASA focused on advanced technology, particularly for its future space missions. And on this slide at the bottom, I have 2 quotes from 2 of those reports. I could have cited any of a half dozen or so reports in that timeframe. But one of the reports from the National Academies in 2009 said that NASA should revitalize its advanced technology development program by establishing a DARPA-like organization within NASA. The Augustine Committee in 2009, an independent blue ribbon committee that was set up to advise the next administration, said that it's time for NASA to reassume its leadership position in advanced technology, in particular for space. So these things were going on, and there was a lot of, in the 2005 to 2010 timeframe, there was a lot of discussion publicly about this. And I'll tell you, for me, whoops, I gotta go back one. For me, it was it was a personal kind of thing. Because I had started my career at NASA Langley as an aerospace technologist. I was focused on technologies that would enable the next generation of planetary missions to Mars, to the outer planets, to Venus. And many of the technologies that I worked on actually in the 1980s and 1990s were just starting to be used in the 2000s and in subsequent years. So I knew that these technology investments were important. Also, I was a professor at Georgia Tech at this time. And while I've taught students at a whole range of levels, one of my favorite things to do was to teach Introduction to Aerospace Engineering at Georgia Tech. This would be a class of about 40 to 60 students mostly 17, 18-year-old kids, freshman year, who are just learning what aerospace is all about. And in that class, we would talk about their dreams of the future in aerospace. Why were they interested in being an aerospace engineer? And I would share with them my view of our space exploration future. And in fact, that's what this slide is. This is a slide from the fall of 2008 from my course materials down at Georgia Tech, where after the students would list the missions that they thought were possible in their lifetime, I would share with the students my list of 9 missions that I felt were big game changers for us in space exploration, space technology, things that I thought were possible. So look at this list, and I mean, it's amazing to me that these are still things that we are working on today, many of which we've made great progress against. Quantifying the causes and the trends, the effects of long-term Earth climate change is a very important aspect of aerospace today. Imagine having the ability to accurately forecast the emergence of major storms and natural disasters, not just a few seconds or minutes before they occur, but hours, to give people in those affected regions time to respond, right? That's the kind of technology that we are on the cusp of achieving through investments in space. One of my favorites on this list would be to identify life elsewhere in our solar system. In fact, one of the reasons I'm going to JPL in about a week is I believe that we are on the cusp of doing this. I believe that our scientific instrumentation that we launch into space is capable enough, or will soon be capable enough, to detect life if it exists in the subsurface of Mars or in the oceans of Europa. And I want to be part of that quest. If you look a little lower on my list, back in 2008, who would have thought that we would be where we are today in terms of commercial low Earth orbit transportation? Back in 2008, that was a dream. There weren't flights like there are tonight. There's going to be a SpaceX flight, right? Today we have SpaceX, we've got Sierra Nevada, Blue Origin, ULA, of course, and many others that are pressing forward with commercial low Earth access to space. This is an area where we have made dramatic improvements, and I would argue that NASA's investments in this area have been something that have made it happen. And so here I was talking to these students about how these things were possible in their lifetime, and I was witnessing NASA's technology budget getting cut. And so in early 2010, when I got a phone call from Charlie Bolden, who was NASA's administrator at that time, and he asked me to come up and visit him, I was like, sure, NASA administrator calls, you got to go visit, right? And in that first meeting, Charlie asked me if I would consider being the chief technologist of NASA. I was blown away, actually. And while it was a very difficult thing for me to think about, because my family was in Georgia, my students were in Georgia, and I certainly didn't want to leave that. The idea of helping NASA in an area that I personally cared about was a huge draw for me. And so I basically started flying back and forth every week between Atlanta and Washington, D.C. for about 2 years. Because this was a passion that I believed in. So what is space technology? Well, space technology to me is a budget line. It's a budget line that didn't exist in 2010. And it's a budget line that was, in my view, incredibly important to create starting in the fiscal year 2011 request for NASA. This budget line was going to contain a spectrum of space technology activities, everything from the formulation of new ideas to ground-based experiments and lab tests, all the way to flight demonstrations for a broad range of technologies that anyone in the country could propose, and if they were competitively selected, could implement all the way to flight. It was originally managed by the Office of the Chief Technologist, and it was managed in a set of 3 groupings. We had the early stage innovation activities. These are your basic research activities, your conceptual design activities. We had technology maturation, where you would get ready for flight And then we had technology demonstration missions where we would actually prove out new technologies in space or in relevant environment. And we were able to get these programs funded. I'll jump to the punch, if you will. And after a couple years, NASA actually formalized these programs in what is now called the Space Technology Mission Directorate. Actually, Mike Kaczarek, who's sitting over here, was the first associate administrator of that mission directorate. And that mission directorate has continued since 2013 to continue to fund a whole series of activities, and I'll talk about a couple of those in just a minute. But what I didn't realize when I agreed, when Charlie Bolden asked me to come to Washington and be the chief technologist and organize these programs, I was still thinking like a technologist. So I thought that meant go canvass the technology community and figure out what the right investments would be and then get those moving, right? Well, it turns out that wasn't the job. The job was actually to convince a skeptical Congress that these kinds of investments were important for our nation's future. So the first thing we did is we built a team in Washington. And as I mentioned at the outset, we had people from all the NASA centers go on detail and come to Washington. We had people already in Washington as part of our team. We had folks from industry or from other universities do IPAs and be part of this effort because they wanted to be part of it on the ground floor. And we had a number of brainstorming sessions in the first few months, and what we spent our time on was not should we invest in propulsion or structures or aerothermodynamics. What we spent our time on is how are we going to manage these programs? What kind of technologies from characteristic space, like they should be broadly applicable technologies, right? Or should they be mission focused? And we settled on broadly applicable technologies. Technologies that had multiple customers. Technologies that industry would be able to use for a commercial advantage, or other government agencies would be able to use to reduce their cost and their efforts in space. We were going to expand the spectrum so there wouldn't be a valley of death, right? And employ a portfolio approach across the technology readiness levels. We were going to use a lot of competition to select these missions because there were great ideas everywhere at the NASA centers, in industry, in academia, and we wanted to capitalize on all of those ideas. We were going to utilize the national academies to review our program and to set up an external review panel to help us manage this program. And overall, our goal was going to be to accelerate the technology base needed for our nation's future in space. Whether those are government missions or industry missions, academic missions, that was irrelevant. We wanted to lay the foundation so that we could do more and more things for the benefit of society in space. And this is an old schematic of what that might look like graphically. If you think about a big funnel of ideas, when you're down in the low technology readiness level area in the early stage innovation on this slide, you can fund lots of ideas when they're conceptual, right? And they're getting 100K or 500K each. Some of those ideas pan out, it turns out, and some of them don't. And so you need a way to select and to filter those technologies as they move forward. There's nothing wrong, by the way, with working on a technology that doesn't pan out. That's what technologists do. If you think that everything you work on is going to pan out, you're in for a rough ride, because that's just not how it works. And some of these technologies, though, that were conceptual ideas, they would mature, and they would need more funding to get tested, to go into ground-based facilities, to go into lab tests, maybe to fly on a sounding rocket. And so that would be the game-changing side, the technology maturation side. And then ultimately, we would want to prove that technology in the relevant environment of space, and we would do so through our technology demonstration missions, right? And that would be the third division, most to the right on this slide. If you think about technology readiness level, and I know many of you here think this way, this is another way of viewing the same thing. We were going to, have a portfolio approach that went all the way from TRL 1 through TRL 6. Okay? In addition, because NASA was going to get back in the technology game, it was going to make us, the agency, a better partner with other government agencies. We could partner better with ARPA-E or DARPA. We could partner with the Air Force on missions. If NASA's only focused on its own programs, then the rest of the government doesn't care about NASA. It's actually through technology that you can develop partnerships where NASA can be, if you will, at the grown-ups table when there are large initiatives being planned. And so because we had the space technology program in this time frame, I'm talking about 2010 to 2012 time frame, NASA became a participant in the National Nanotechnology Initiative, in the National Robotics Initiative, and in many other cross-governmental activities. And this is something that's been a positive aspect of space technology, the investments that NASA is making in space technology all along. So for example, in 2014, if you go forward in time, in that year, the Space Technology Mission Directorate had 45 different activities that it was doing in partnership with other government agencies, 10 activities in partnership with international organizations. And there's a list of a few of them on this slide, everything from our green propellant mission that we're doing in partnership with the Air Force to a solar sail demonstration mission with NOAA, on down the line. This is a way for NASA, as I said, this is a way for NASA to engage others and to grow the pie. And that was another goal of the Space Technology Mission Directorate. Now, I mentioned that when I went there, I thought I was going to be all about technology, and I wasn't. And that was a big shock to me. It turns out that when the president creates a new program, he doesn't actually provide the funds. Probably some of you knew that. The Congress provides the funds. And so when I arrived, my first day was February 1st, 2010, which was the day the 2011 budget was rolled out. I arrived and we developed this portfolio of programs in my first few months. I then had to spend many months walking around Washington, taking every meeting I can, really running around Washington like a chicken with my head cut off, actually, taking every meeting I could to get other people engaged, to get them to understand why these investments were important. And it wasn't just me doing this. Over time, there was a whole coalition of people who were writing op-eds, who were writing reports, who were giving Congress their input. Various companies, universities did this as well. And here's just a sampling. The budget came out, as I said, on February 1st, 2010. It was President Obama's first budget, so it was a budget from a Democratic administration. And what was interesting to me is that Newt Gingrich and Bob Walker, two very prominent Republicans, came out in support of that budget. And they came out in support of the budget because at its heart, it was a budget about advanced technology, which was something they felt was important for NASA to move into the 21st century. And so they wrote an op-ed in February of that year. Later on that year, Bill Ballhaus, who had formerly run the Office of Aerospace Technology, and Ray Colliday, who had also run that office, together they wrote an op-ed that was in Space News. And in their op-ed, they talked about this advanced technology program and how it needed to be the cornerstone or the foundation upon which NASA's new missions could be built, and it needed to be started right now. That was a really important op-ed because in the September timeframe, all of these latter quotes are from September 2010. In that time frame, that's when Congress was making its decisions about whether this nascent program would actually even exist or not. And so getting support in this way, getting support from some Nobel laureates who wrote a letter, and getting university support. We got a large number, 15 universities who came together and wrote a letter of support for this effort as well. And these kinds of things are very effective in getting congressional support for your new programs. So I was a technologist who had to learn this game, right? This game of advocacy in Washington. And while I was there, I met with as many members of Congress as I could. I went to all the relevant committees. And in May of that year, we started to get the markups from those committees, and it looked like space technology was going to get to exist. It started to appear in legislation, right? They would say things like there needs to be an ARPA-S, ARPA space element of NASA. Or a long-term space technology research and development activity is important for NASA to include. Advanced space technologies and systems that are independent of specific spaceflight missions should be included. Over on the Senate side, about a month or two later, they started talking about advanced multi-purpose technologies that could enable new approaches to NASA's current missions. And on the authorization side in the Senate as well. Now this took a lot. There were a lot of conversations. This was not the first response from Congress, right? But over time, our team enabled this response. And then as the year wound up, we had the NASA Authorization Act of 2010, which included space technology in it for the first time. And this meant that our new program was authorized in the law. It was authorized to exist, is what that means. And then at the end of that year, in December, and what's important here is that by December of 2010, the House had flipped Republican. So if you can think back to the 2008 timeframe when President Obama started his presidency, both the House and the Senate were Democratic at that time. But in 2010, the Republicans took control of the House. And that was important because our team, we didn't know the difference, frankly, between Republicans and Democrats. We just knew they were all members of Congress and they were all important. And so we had talked to all of them. Every single one that would take a meeting with us, we had talked to. And so when the House flipped, it didn't affect us. And in the final Appropriations Act, which was done through a Republican-led House and a Democratic-controlled Senate, space technology was funded. And so by December of 2010, the space technology program existed and it had its budget. Now, it didn't have the budget we wanted, but it had its budget. So our goal was to get, in that first year, was to get $572 million. I'll never forget that number. $572 million for space technology, and we got about $350 million. And our long-term goal was to get $1 billion a year for space technology efforts, about 3-4% of NASA's top-line budget for these efforts that were going to enable our future success, our future missions. So this slide here shows you space technology's appropriation history. And you can see that after I left Washington, they did much better than while I was there. It's okay. So there's my first year at 350, and then we got up almost to 600 million in my second year, and then Mike Kazarek took over, and he did pretty well getting the budget up above 600 million, approaching 700 million. Then Steve Jerzik took over, and he did even better. Sorry, Mike. He did even better, got it up a little higher, and then just this year, for the first time ever, space technology crested $1 billion mark, which was our original goal. So, and none of this, by the way, as I said, would be possible without lots of people working in the government, in academia, in industry. Now, this top line support for space technology, it's grown, and that's a good thing. Most of you that are doing space work that are here at this conference are probably space technologists. That support was only possible because this has been a bipartisan thing. Whether you're Republican or Democrat, it doesn't matter. If you believe in a future in space, then the idea of investing in that future to create new missions, grand missions, both of human exploration and of science, discovery, and of commerce, that's something that you probably believe in. Now, one of the things that I'm a little disappointed in is space technology is today our primary area of engagement with academia on the space side. And yet the space side, if you look at one of those pie charts, the academic portion of the budget, at least in FY19, is about 9% of the total space technology budget, and that's about 4% of the agency budget. So overall, you're talking about 0.4% of the agency budget. I think that's still a little bit low, personally. But overall, it's pretty good. If you look at the pie chart on the right, you can see that about half of the funding is going to industry, and about 40% is being led out of NASA still. That doesn't mean that NASA doesn't farm that out to industry or to academia. They do, but this is just where the funding starts with initially. Industry was a big part of this activity in the beginning, and if you fast forward to 2014, you can see that industry is still heavily engaged in the program. In 2015, the program began to innovate, come up with new ways of infusing technology in missions. I love the tipping point technology solicitation and the collaborative opportunity solicitations that were started in about 2015. NASA's now made over 75 awards through these two activities. A tipping point technology, by the way, is where industry proposes an idea for, it could be a commercial product, and they're almost on the verge of getting that ready to flight. They're at the tipping point, if you will. And so they need just a little bit of help from NASA, and so they can propose and be competitively selected based on economic return for that investment. And a collaborative opportunity solicitation means this is something that NASA will partner with industry on, where they'll provide workforce or facilities for industry to use. These on both sides of the ledger here, whether you're talking about tipping point or the collaborative opportunities, these have all been very significant. You can see they're going to a broad range of industry partners, and these industry partners, frankly, are the strength of our U.S. space economy. And so supporting them, fostering their growth is a big element of why NASA exists and what NASA should be doing. In this past year, in 2019, the Space Technology Mission Directorate evaluated over 35,000 proposals, made over 700 selections. Of those selections, they included about 350 partnerships with universities, about 100 different universities in that 350 selections. They have about 1,000 active technology projects going on right now. They have more than 2,300 software releases that they've made that are publicly available from the Space Technology Mission Directorate, and they have hundreds of industry collaborations. And over the lifetime of space technology, over this decade, they've got about 50 technologies that have already either been flight demonstrated or are about to be flight demonstrated the next couple of years. So I'm just going to walk through a couple of these quickly. In the early stage innovation category, this is where most of the university activity is. There's a number of programs. I'm probably most proud of the Space Technology Research Fellowship activities. There's been over 500 graduate students who have had their PhD work funded via NASA through the Space Technology Research Fellowship Program. You can see on the right-hand side that those students are all throughout our community today. If you take the ones that have graduated, there's about 240, 250 that have graduated to date. You know, some of them are back in academia. In fact, a couple of them that are in academia have their own Space Technology Fellowship graduate students. So the cycle is permeating, if you will. A good bit of them are in industry or at NASA centers. There's also been a number of early career faculty that have been funded this way. And the most recent innovation here is the Space Technology Research Institutes. There's just been a couple of those, but these are larger multi-university activities where NASA really wants to make a big bet and go forward in a particular technology area. I think the early stage work of this program has been very successful. Some of my favorite technologies, you know, there's 1,000 of them, so I can't go through them all with you, but a couple of the things that have been really, to me, impactful. I think about the Composite Cryo tank activity that was started back in 2010, 2011, and then was successfully demonstrated a couple years later down at the Marshall Space Flight Center. These are composite cryo tanks storing hydrogen, very low temperatures, very high pressures. This is something that cost us the X-34, if you go back in history, right, as we didn't have the technology to do this now. DARPA is counting on this technology in their XS-1 spaceplane program, and this is something that DARPA could use in the future, or that could be available to NASA or its commercial partners based on this work. Probably my favorite space technology story is heat. I think Raj Venkatapati might even be here. Oh, there's my friend. Hi, Raj. So Raj Venkatapati from NASA Ames proposed the HEAT, or something like the HEAT thermal protection system, through the SIF program, the Center Innovation Fund. So each of the NASA centers had a very small pot of money where for something like $10,000, a researcher at NASA could get a little bit of seed money and pursue an idea. And Raj had this idea, and the center chief technologist at NASA Ames thought it was a good one, so he got a little bit of money through that Center Innovation Fund. And it turned out it was a good idea. And so later on, Ames proposed it through the game-changing program. It got some more funding. And now this material is actually going to fly in several of NASA's more significant missions. It's part of the Orion capsule. It's part of the compression pads for the Orion capsule. And it's also baseline for flight on the Mars Sample Return Earth Entry Vehicle, the mission that will bring samples of Mars back through our atmosphere here in the Earth in about, 10 years. Is planning to use this material. It's available for Venus missions and outer planet missions as well. And all of this started with a $10,000 investment by a chief technologist at a center. I mean, it's really a remarkable story. If you want to know more about it, Raj is here. You could talk to him about it. Space technology's done very well in the solar power area as well. The rollout solar arrays that were developed in the 2013-2014 area timeframe were tested in 2017 on the space station and are now baseline to fly on APL's DART mission in the next couple of years, the asteroid redirection test mission. And these, a different company, but a similar idea, put movable solar arrays and a movable antenna on the Marco small sats. Marco enabled the return of real-time data during the InSight landing. Any of you saw the InSight landing, everybody jumping up and down with the success, right? Well, how would you have felt if you knew that that mission was happening, but it was going to take several hours, maybe even half a day, to get the data back? Well, that was the plan. But Marco, a small spacecraft that was kind of a risk in itself, outfitted with this technology, was able to position itself at a point in space where we could get real-time communication with InSight. Also to prove the viability of small spacecraft in interplanetary space. A pretty significant feat itself. Going to some of the bigger missions, we've got the Deep Space Atomic Clock, we've got the Green Propellant Infusion mission, both of which are in space today. Deep Space Atomic Clock is going to enable autonomous operations of deep space satellites in the future, deep space spacecraft in the future. To get accurate position navigation, you need good timing. And basically, that's what the atomic clock is doing. And then you have the Green Propellant Infusion mission, which is led by Ball Aerospace in conjunction with the Air Force, which is proving a non-toxic propellant substitute to hydrazine. Those of you in the propulsion world that are here know we use hydrazine a lot. Hydrazine is very toxic, difficult to handle. This propellant that was originally developed by the Air Force and is being proven through this mission has a much better density than hydrazine and a slightly better ISP. And so far, it's proving out in this flight demonstration to work remarkably well. And we could probably use it on a number of upcoming missions. There's a whole series of other technologies that are being developed. In-space assembly, manufacturing advances. Probably my favorite here would have been the robotic refueling mission that led to the Restore-L mission that's currently in development at the Goddard Space Flight Center. There's a whole series of industry partnerships that space technology is funding in the cryo fluid management area. And these activities are incredibly important for space transportation, whether we're talking about launch or propellant depots or in situ resource utilization. You know, the ability to manage cryo fluids, transfer them in space, is going to be part of our economy in just a couple of years. So I know that was a quick rundown, but what I'm really trying to get at and make sure you're aware of is a couple things. If you want to be a good technologist, then yes, focus on your technology. Be the best technologist that you know how to be. But every once in a while, get out of your lab and go to Washington, because someone needs to know about your technology, right? We were at a point in time at NASA where space technology investments were so small that they were hard to find, where the research champions at the NASA centers and elsewhere around the country didn't have someone in Washington who was their champion, who was their representative. And in 2010, with the creation of the space technology programs that became the Space Technology Mission Directorate, that all changed. These programs are now the central NASA contribution to a revitalized research, technology, and innovation agenda for our nation. And if you think about it, what they do is they balance NASA's long-standing core competencies: research and technology, spaceflight hardware development, and mission operations. They don't all need to be funded equally, but they all need to be funded. They all need to exist at NASA. And what the Space Technology Mission Directorate is really all about is accelerating the technology base required for our future missions in space. Doing so is good for NASA, it's good for our US industry, but also it's good for the economic competitiveness of our nation. It's good as an inspiration to young people who want to go into these fields in the future. And it's also a way that we demonstrate how aerospace applies to everyday life. Right? How many of you have used an example about GPS when talking to your grandmother? Right? Maybe not your grandmother, but to your parents, perhaps. Space technology is prevalent in our society. It's making more and more of a difference in our lives every day, and NASA's investments in advancing space technology are critical to the future of our nation. With that, I want to thank you for your attention during this seminar and see if there are any questions. Thank you very much. You take questions?
Thank you, Dr. Braun, for such a fitting tribute to William Durand. Right now, we have time for 1 or 2 questions the audience might have. Please use the microphone as it's set up for you there. Go ahead.
Yeah. Ian.
Repeat the question.
So the question was, of my list of 9 things that was back in 2008, that I would talk to students about, give us a couple new ones. I'm not going to give you a couple new ones, but I'll do better than that. So back in 2008, on my list was identify Earth-like worlds around other stars. And that's been something, by the way, that's been a mind-blowing passion of mine. I can't believe that it's actually even possible, right? Like back in 2008, when I would look up in the night sky, I knew that there were planets around other stars, but I couldn't prove it. Well, just the other day, I was walking at the Jet Propulsion Laboratory in Pasadena, and in their headquarters building, they have a counter. They have a metal counter on the wall, and it says 14. They've actually identified 14 Earth-like worlds around other stars. So these are generally Earth-sized, thought to have a rocky core, thought to have significant water on the surface, right? That's the definition of an Earth-sized planet. That's remarkable that in 10 years we went from 0 to 1 all the way up to 14. Of course, there are hundreds, thousands of other planets that are known around other stars now. But if you think back 10 years, 15 years, we didn't even know that, right? So that's an example of tremendous progress. I think on the commercial spaceflight side, there's been tremendous progress. The 2011 budget, I should point out, was also the budget where the Obama administration doubled down on the Bush administration's priority for commercial space. And that led to the cargo missions and the crew missions that we're seeing now, and led to the great advance that's occurred in US industry over this 10-year time period. The one that I'd like to see more of, just so you know, is energy. I have it on there, solar energy from space. I'm still a big believer of that. I think we're getting pretty close on the technology, but we haven't really made huge advances there yet. It's coming.
All right. Thank you, Dr. Braun. Unfortunately, we're out of time for questions.
No problem.
At this time, I'd like to ask Joe Landon to join me up on the stage again, and we'll present Dr. Braun with the award. On behalf of AIAA, it is now my privilege to present to you with the Durand Certificate and Medal.
Thank you.
Thank you for being knighted.
Wow. Congratulations. Thank you. That's awesome. Thank you. Thanks, man. Wow. Now we gotta get together. Yeah. Thanks.
All right.
All right. Yeah, thank you. Thank you all. Thank you. Thanks, Jim. Wow.
Thank you, everyone. That concludes today's lecture. Enjoy the rest of the conference.